Hello, and welcome to our short video example of how the leading performance and expanded portfolio of United Silicon Carbide's Gen 4 silicon carbide FETs offer design flexibility to best meet your product requirements. United Silicon Carbide now offers 13 discrete 750 volt FETs spanning from 6 milliohm to 60 milliohm in its new Gen 4 series. In this example, I'll walk you through the discrete FET options for the fast leg switches in a bridgeless totem-pole PFC circuit. We're illustrating the performance, cost, and thermal considerations across our G4 750 volt FET portfolio. This example is just one of many designs that can be evaluated with our FET jet calculator found on our website unitedsic.com. We consider a power level of 3.6 kilowatts and a fast leg switching frequency of 65 kilohertz. The plot shows the normalized distributor pricing on the left y-axis, and on the right y-axis, we're showing the difference in junction temperature compared to the lowest RDS on part considered, which is the 18 milliohm 750 volt UJ4C 075018K4S. With the 18 milliohm part, we see a semiconductor efficiency of 99.4% and a modest junction temperature anticipated at 96 degrees C at full load. The FET offers excellent performance at full and partial load. If we now consider the next higher RDS on part in the series, being the 23 milliohm FET, we notice again an excellent performance with a semiconductor efficiency of around 99.4%. This comes with a slight temperature increase compared to the 18 milliohm part of about 2 degrees C. However, this will come with a roughly 20% cost savings in the fast leg FET. This part offers well-balanced losses with a conduction and switching loss split of roughly 50-50. Moving up in the portfolio to 33 milliohms, we can again achieve a good performance of 99.3% semiconductor efficiency, but now with more than 40% savings in fast leg FET cost. This represents an excellent cost-performance design point. The anticipated junction temperature is still a manageable 102 degrees C, but the conduction losses at 3.6 kilowatts are beginning to dominate the total. Roughly 2/3 of the losses in the fast leg switches are now conduction losses. As we consider yet higher RDS on parts, we move to the 44 milliohm FETs. Here we begin to see that the full load efficiency drops to 99.1%. And the smaller die size with larger thermal resistance and higher conduction losses raises the junction temperature to 108 degrees C. The conduction losses now represent 75% of the total fast leg loss. The cost savings here, compared to the most efficient 18 milliohm FETs, is roughly 45%. These parts are a good choice in applications where the partial or mid-load efficiency dominates the overall PFC operating losses. If we look at the same example at a power level of 1.5 kilowatts, then the 44 milliohm and 60 milliohm G4 silicon carbide FETs stand out as excellent design choices. They offer comparable semiconductor efficiency as their larger, costlier counterparts, but at roughly 50% of the fast leg cost. At 1.5 kilowatts, the 44 milliohm and 60 milliohm FET offer balanced switching and conduction losses, and a low anticipated operating temperature of about 93 degrees Celsius. United Silicon Carbide's full portfolio of high-performance G4 750 volt FETs allow users to design better for their customer application requirements. Designers no longer have to make up large compromises in power handling capability, thermal system complexity, or large price jumps associated with a more limited portfolio. If you'd like to see what United Silicon Carbide's new G4 silicon carbide FETs can do for your applications, visit our FETJet Calculator 2.0. It can be found at our website at www.unitedsic.com. There you'll find instant results to your fundamental design decisions. All the key power topologies are included, and no registration is required.